So chapter 4 is called Carbon and the Molecular Diversity of Life. And so we're basically, now that we learned all about chemistry in general in chapter 2, and then the chemistry of water in chapter 3 and all the special properties of water, next we're going to move on to carbon. Because water is really important, but carbon is what the molecules of life are made of. So the beginning discusses how carbon is the backbone of life. So like we said in the last chapter, water is the medium where life can happen. Water, or life, needs water. There could be no life if there wasn't water. We're made up of mostly water, but all of the molecules that have anything to do with life and living things and what we need to process everything our cells do, they're made up of carbon, or carbon-based compounds. And this is for a couple of reasons. Carbon is very special. It has a couple of very special capabilities which allow it to provide life to so many different kinds of living things. And proteins, DNA, carbohydrates, and other molecules that distinguish living matter are all composed of carbon compounds. So basically, anything that we associate with living things has carbon in it, like this moose. So the first section is called Organic Chemistry, is the study of carbon compounds, and it talks a lot about how this was discovered. I just want really quickly for you guys to know that when we talk about organic chemistry, it's things that have to do with living things. And anything organic means that it has carbon in it, and carbon's bonded to hydrogen. So for example, CO2, carbon dioxide, obviously has carbon in it, but there's no hydrogens in there. There's no carbons bonded to hydrogens. And obviously CO2 is essential for life. Plants use it to make glucose, etc., which we need to be alive, but it's not an organic compound. Organic compounds almost always have C's bonded to H's, carbons bonded to hydrogens. And they can be tiny, tiny molecules, smallest one being CH4, which is methane, which is carbon bonded to 4 hydrogens, up to gigantic chains of DNA or huge proteins that have carbons and hydrogens. Most organic compounds contain hydrogen atoms in addition to carbon atoms. We don't need to know this. Okay, so then, in addition to the C's and the H's, there's also often usually a couple of other elements which are found in most organic, or commonly found in organic molecules. These are oxygen, nitrogen, sulfur, and phosphorus. So CHONSP are what most organic molecules are made up of. And carbon atoms can form diverse molecules by bonding to 4 other atoms, is what the next section is about. And this is why life is possible, basically. So an electron configuration is key to an atom's characteristics, because think of it, remember back to chemistry. So the number of electrons in a valence electron shell are what can interact with other atoms and give an atom its characteristics. So if an atom has a full octet in its outer shell, it's not going to react very strongly. If it has 7, it's going to react differently than if it has 1, if it has 2, 3, etc. Because the electrons are what form the bonds, and that's what interacts between different atoms. Carbon, so electron configuration determines the kinds and number of bonds an atom will form with other atoms. So carbon has 4 valence electrons. So it has 4. It's pretty stable, but what it does is it shares those 4 bonds. It makes 4 covalent bonds because it needs 4 more to have a full octet. So the best way to get there is by sharing 4 and getting 4 in return. And because of this, we can have huge organic molecules because it can bond with a lot of different kinds of molecules in addition to up to 4 at one time. And it can form single or double bonds, so this also gives it more diversity. And the fact that it can bond with 4 other atoms allows crazy branches to happen, because it can, if we have a central carbon atom, it can form bonds with 4 other atoms and make a very 3-dimensional sort of molecule. And so if a molecule is bound to 4 things, we say it has a tetrahedral shape. So that would be this right here. So see, this is our carbon in the middle. It's bonded to 4 hydrogens. That's called a tetrahedral shape. That's like a triangular pyramid, basically. And this is the most simple shape of something bonded to 4 other things. And the bond angles, which you won't really need to know, but it's good to know. You'll need to know this for organic chemistry in college. These bond angles, like between here to here, is 109.5 degrees. And that would be the same with any atom bonded to 4 other, single bonded to any other 4 other atoms. Then this can also happen if we get a little more complex and we have 2 carbons and they're each bonded to 3. This is 2 tetrahedral shapes. So there's a tetrahedral shape right here with this carbon and a tetrahedral shape right here with this carbon. So even though they are, we got a little more complicated, this atom is still bonded to 4 other atoms, and this atom is still bonded to 4 other atoms. So all these bond angles would still be 109 degrees. Whereas down here, when we throw in a double bond, now we're flat because the double bond can't rotate like these bonds can. So right here, these 2 bonds could rotate around each other, right? But these 2, they're stuck. It's like a chain. You can't rotate them. So now this doesn't, it's not 109 degrees anymore. It's totally flat. So, like it says, the electron configuration of carbon gives it covalent compatibility with many different elements. Don't worry about the last bullet point. Okay, so all these other molecules have available valence electrons, right? And so the number of valence electrons defines how it's going to bond with carbon. Okay, so carbon atoms can partner with atoms other than hydrogen. So we know carbon dioxide is double bonded to 2 oxygens. And this one is totally flat because it has double bonds and those can't rotate, right? Whereas urea is carbon bonded to nitrogen and oxygen. So this is still an organic molecule because we have carbons and hydrogens, and it's found in all living things. And but we can still see that carbon has 4 bonds. 1, 2, 3, 4. Each of these dashes represents a line, which I hope you know from chemistry. So we have, since we know carbons can form bonds with each other, we can get really, really, really long chains. And this is called the carbon skeleton of a molecule. Because think of it like your bones. Your bones are in the center and support everything, and then we have lots of different things coming off of our bones. Same things with the carbon skeleton. Carbons are in the middle, they provide the backbone, and then we can have lots of different groups coming off of the carbon skeleton. They can vary in length and shape. So for example, this ethane is pretty short, just 2, whereas propane's 3. They can have up to like thousands and thousands of carbons. And then they can also be branched. They don't have to be straight. Because remember, carbon can form up to 4 bonds. They can go in lots of different directions. So they can be straight or branched. They can have double bonds but be in different places. So here's 4 carbons, but here the double bond is in the middle, and here the double bond, on the side, and here the double bonds in the middle. Or they can form rings. So there's lots of different ways we can get different carbon molecules. Fix all of those things again. And then we have these things called hydrocarbons, which are organic molecules which only have carbon and hydrogen. Hydrocarbon, carbon, hydrogen. Pretty obvious. Many organic molecules, such as fats, have hydrocarbon components because hydrocarbons are nonpolar. They share their electrons almost entirely equally, so there's no partial charges, so they don't form hydrogen bonds with everything around them, right? So they do not blend in with water because they don't form those hydrogen bonds, which is why oil and water don't mix together. But these hydrocarbons can undergo reactions that release a ton of energy, which is why our fat stores energy for us, which is why gasoline is a hydrocarbon, and that releases energy to power your car. So this is human fat cells. Adipose is a kind of fat cell, and here are long hydrocarbon chains. And then a couple other things to talk about. Isomers are compounds with the same molecular formula that have different structures and properties. So structural isomers are different molecules that have the same exact number of atoms. So here we have 5 carbons, and 12 hydrogens, but they look totally different. So these are structural isomers from each other. Then we have these things called cis-trans isomers, which mean that what we have around a double bond is flipped from each other. So remember how double bonds can't rotate. So if you have hydrogens on this side, this can't rotate, so it's stuck like this, and will probably have different properties than if we had hydrogens on the other side. So they're called cis-trans isomers because that refers to which side of the molecule we have these X's, which are groups of other atoms. So on this one, the cis isomer, they're on the same side. On the side trans, they're on the opposite. So cis means same side, trans means opposite side. Then we have enantiomers. And this goes back to that tetrahedral shape we talked about earlier. Because remember that carbon can form bonds with up to 4 things. So if it's forming bonds with 4 different atoms, they will be mirror images of each other, or they can be mirror images of each other. So here we have carbon is bonded to a methane, bonded to an ammonia group, NH2, bonded to an alcohol, COOH, and bonded to a hydrogen. Sorry, that's an aldehyde, not an alcohol. So 4 different things: gray, blue, red, white. Now, if we flip any of these 2, now we have a mirror image of each other. And it's easy to see because if you rotated this one, sorry, you can't see where I'm pointing. If you rotated this one this way, now the blue is facing towards you, the white is facing towards the back, and this methane is facing towards the right. So you can never get them to be the same. They're always going to be mirror images of each other. And these are important because they can have similar but different enough effects enantiomers from each other. So for example, 2 enantiomers of a drug may have different effects, and usually only one isomer is biologically active. So for example, ibuprofen is used if you have a headache, or it's an anti-inflammatory, and albuterol is used if you have asthma. So, they are, but you need to have the right enantiomer. So this S enantiomer is effective, whereas this R enantiomer is ineffective. And that's all you need to know about the carbon skeleton.